We're going to talk a little bit about normal models today, and I'm going to really try to focus on some of the vocabulary. You all have this inherent idea of what a normal model looks like, but I want to really clarify something for you today. If I were to measure fish in centimeters in a place called Kingsman Reef, I could graph the lengths of all the fish, and what I would get is I would get a histogram of data. Notice the histogram is rough, it has jagged edges. Sometimes we look at that and we say, hey, it almost looks like I could superimpose on it a really smooth bell-shaped curve. And that is what we see over here. That bell-shaped curve, which has specific proportions, is called the normal model. The histogram is raw data. The model of the data is like a theoretical perfection. So in terms of vocabulary, we're going to go between the distribution, which is the histogram, and the model here, which is the normal model. So for example, distributions are made of real data. A model is theoretical values. A real distribution is what we observed. It's the actual lengths of the fish. The model is what we imagine it would look like if it were a perfect world. The distribution is known. We can measure those fish. A model is unknowable. A distribution, we make graphs like histograms or stem plots, box and whiskers. A model is a math curve. It's actually a physical curve and it has an equation. There is an equation for the normal model. And then for data that's in a distribution, we calculate statistics, versus a model, we calculate parameters. And you're probably saying, well, what's the difference between a statistic and a parameter? Well, let's just say that we start off here and we have a population of people and say it's all New Yorkers. And we want to get the height of the average New Yorker using all New Yorkers. Well, that would be a ridiculously hard thing to do. We know that height exists. The height of our population, all New Yorkers exist. We really can't know it though. And so we call its mean the Greek letter mu, versus if I took a sample and I took maybe 100 people and I calculated the mean of that sample. The parameter is the numeric summary that we have of the entire population. So parameters are numeric summaries, and I'm sorry for my messy writing there, that is a U, of a population. A statistic is numeric summaries of a sample. Now, think about it this way. Parameters are about populations, which begin with the letter P. Statistics are about samples, which begin with the letter S. Statistics are knowable. We're calculating them from a sample. Parameters can be about really large populations sometimes, so a lot of times they're unknowable. For parameters, we use Greek letters, believe it or not. And my saying always is, we use Greek letters because of only the gods know them. So a parameter is for the mean, we would use mu. A statistic is for the sample, we would use x bar. Both of these are means, but one's of a population and one's of a sample. Same with standard deviation. For an entire population, I use the Greek letter sigma. For a sample, I use the little letter s. Okay, ready for the next page. Okay, you all have this idea of the normal model, and we have this idea that we superimpose it on these histograms that can be ugly, but we get this idealized curve. And this idealized curve is centered at its mean. Notice I'm using mu because this is theoretical. Only the gods know it. And what we like to do is we like to count out standard deviations from the mean. For example, we might go 1 standard deviation from the mean in either direction, and we know that would be 68% of the population. We might go out 2 standard deviations from the mean, and that would encompass 95% of our population. And we could actually go out 3 standard deviations from the mean, and that would encompass 99.7% of our population. These percentages you need to have memorized: 68, 95, 99.7 rule, or some people call it the empirical rule. Now, many times you want to be able to identify where 1 standard deviation from the mean is. One way to do this is to look for what we call in upper level math a point of inflection. This is where a curve goes from being concave down, if you think of it, it's like a cup that doesn't hold water, to concave up, where it would hold water. That point where they meet is a point of inflection. If we look at this graph here, it looks like it's a down cup, it wouldn't hold water. And then around here, it switches to an up cup that would. That distance from the mean is 1 standard deviation. And we can see it on both sides. Okay, now again, I just kind of want to point out to you that when we're playing with normal models, that 68, 95, 99.7 has to stay the same. You know, there's lots of things I can do. With the curve, I could shift the mean and move the actual curve. I could even like switch the standard deviation, and I'm just trying to grab this here and show you as I make that distance from the mean get larger, the normal model gets short and squat. As I make that 1 standard deviation get smaller, do you see how the curve is getting really tiny and thin? So a standard deviation basically tells you where, or actually how fit or fat it is. You could have a very thin normal curve or a very fat normal curve, but in there, the distribution or proportions like 68, 95, 99.7 will still stay the same. Okay, with that said, I'm going back here. We're going to play with something called the flight simulator. This is kind of cool. I've included the link so that you can play with this yourself too. And what this does is it lets us go and just kind of play this little game where it times us to see how long we can hold that red square and move it without touching the walls or the blue blocks. So like here, oh, I'm doing it. I survived 3.963 seconds. I warn you when you try this, it's really addictive. Now, going back to our lesson, they claim in this game that if you took all of the times that people who play that game got, that they would follow a normal distribution with a mean of 15 seconds and a standard deviation of 3.75 seconds. Now, I want again to stress to you, the actual data of the times is going to be a histogram, but we superimpose on it a normal model. And we're saying that the normal model that we superimpose on it is centered at 15. And I hit the wrong thing, so let's go over there. 15. We don't want a yellow letter. That would be number. That would be great. And so when they ask you on the homework to draw and label a normal model, we start off with the mean. And from that mean, we move 1 standard deviation to the right, 1 standard deviation to the left, and we know that this should encompass 68% of the data. Now, if the standard deviation is 3.75, if I add 15 plus 3.75, I got 18.75. And if I subtract 3.75, I get 11.25. What this means is that 68% of the scores are going to be between 11.25 and 18.75, and I believe these are milliseconds. I could be wrong there. If I go out 2 standard deviations, I'm just going to add another 3.75, which puts me at 22.5. And on the other side, let's see, 7.5. And if I go out those 2 standard deviations, I should be hitting 95% of people's times. And if someone is incredibly, incredibly good, we would go out 3 standard deviations, which if I add another 3.75, I would get 26.25. And on the other side, I would get 3.75. And if I go out those, I should have hit 99.7% of the scores of the people playing that game. Now, I want to note for you something. There are some people that are going to not fall within these ranges because of unusual things happen. Okay, and so you want to remember that the normal curve, it really extends on forever, approaching these axes, which would then become asymptotes. Now, I'm going to ask you some questions using these pictures. I'm going to ask you to answer the following 3 questions, and I'm going to then ask you to turn off the video and check your answers. First one is, what % of games lasted between 7.5 and 22.5 seconds? The second, what % of games are less than 11.25 seconds? And the last one, what % of games are more than 22.5 seconds? Turn off the video, try these, and then we'll check them. Okay, here goes. Between 7.5 and 22.5, you can see clearly from the picture, those are both the green numbers, that represents 95% of the people who played the game's scores. Now the next one is, what % are less than 11.25? What I like to do when I do this one, and I'm just going to use a highlighter here, is less than 11.25. Just think of it this way for a second. 11.25, if you go in both directions, hits 68% of the score. That means that 32% is left for these 2 tails. So if I only want what's less than 11.25, then what I'm really saying is I want half of what's left. So 100 minus 68 gives us both blue tails. Divided in half gives us 16%. And then the last one says, what % of games are more than 22.5 seconds? Now I can follow a similar idea here. I'm going to move this out. Oh, doesn't want to move. Okay, let's move it there. Let's move that there. And let's bring this area out here to 22.5. What I've just done is in both sides, I've now gone out 2 standard deviations. That means what's left above it and below it is 5%, and I'm taking half of that, so the answer to the last question should be 2.5 seconds. And with that said, I've kind of given you a good feel of what you're going to need for this section. What did I say here? That's 2.5, and I'm having trouble getting it back to the original one. And let me see. I'm going to go to pen, 2.5%. The big keys I want you to get from this video are that, 1, the normal model is a model. It's theoretical perfection. 2, parameters, which we use Greek letters for, are means and standard deviations in any summaries that we make of a population. Statistics are for samples, and you should know the 68, 95, 99.7% rule for normal models.